Previously, we talked about Ampere's law, where we found the magnetic field outside the current carrying wire. Now we are looking for another application, and we are finding the magnetic field inside a thick current carrying wire. Okay, so the orange loop you can see is the path integration, and we are finding the magnetic field on that orange circle, any point on it. And as you can see, it is symmetrical, so it's concentric with the wire. That makes the magnetic field uniform along this path, and it's going to be the same magnitude any point on that orange line. And once again, we are applying Ampere's law, and we are writing starting with the integral of b dot ds, and that is mu naught I enclosed. So in this case, I enclosed is a little different than what we had before, because earlier we had the Amperian loop, that orange loop, kind of covering up everything, right? All entire current. So it was easy to replace I enclosed with simply I. But now I is the total current, and it covers that entire blue area. And right now the area we need to take, the cross-sectional area that I'm talking about is not the whole thing, so it's just this part. So we need to figure that out. So this is the case for a uniform current density. Okay, we will talk about what happens if current density is not uniform. So remember the current density definition, it is the current divided by the cross-sectional area. I'm going to call this one total area, and this I is the total current. Okay, so we need to use this, and since current density doesn't change, we can do that for the enclosed part. So the enclosed current divided by the area, the cross-sectional area defined by that Amperian loop. So I don't want you to confuse this. This is not an area, that is a path integration. Okay, in the Ampere's law, we are doing this integral over a path, not an area. But to figure out I enclosed on the right side of that equation, I need to think about current density. And since current density is uniform in this specific case, then I'm going to use the current density definition, and I'm going to find the kind of the effective area, or let's call it enclosed area, and kind of use this ratio to relate the current to the enclosed current. So when we work on the Ampere's law, what we have is then on the left side we have b ds cosine of the angle between them. You can see that they are pointing the same direction, so the angle is 0. And mu naught, and I'm gonna replace I enclosed now from that new ratio that I obtained from the current density. So the I enclosed would be the current I, as you can see, and then I enclosed, the area enclosed over total area. So the area enclosed is the area using that little r, right? So it's going to be pi r squared. That is the area right here. That is the enclosed part, enclosed by that Amperian loop. Okay, and that's the cross-sectional area. And divided by the total area, and that is the, as you can see, the blue shaded area. So it's the entire wire's cross-sectional area, and that is going to be pi. And now I need to use that capital R. It's going to be pi r squared this way. So a couple things here. Cosine 0 goes to 1, and pi's are going to cancel out, and b is uniform, it will come out of that integral. So ds is going to go to the circumference of that orange line, orange circle. So when we put these together, we have b ds becomes 2 pi r. Again, since we are using the orange circle, now this is the r, so you gotta kind of pay attention to all those details. I'm writing the circumference of that orange circle, and the radius is little r, not big R. And that's equal to mu naught I little r squared divided by capital R squared. Now, one of those little r's are going to go away, and I can write the magnetic field as mu naught I r little r divided by 2 pi r squared. Okay, and this is the magnetic field inside straight wire. Okay. Again, this is an application of Ampere's law. You do not need to memorize it. You can find out, and you should be able to do this your own. And we will solve an example where J is non-uniform. This was a little easier because we could just use this, but if it is non-uniform, remember the integral for J. We are going to use that to figure things out.